So when I finished my last video demonstrating the GD&T Position Calculator that I developed in Excel, I realized there's a few things I want to clarify that I probably didn't explain well enough, and a couple of things I neglected to mention. So let's just follow up and wrap up with the GD&T position error. So first thing I wanted to do, is go over the style of the different callouts you can have. So in the last presentation, I kind of mixed some of the different callouts that you might have seen, and I may have been referencing maximum material when it wasn't called out. So I wanted to clarify what these different callouts mean specifically. So when you're looking at position error in the feature control frame, first thing is going to be the symbol for position. Your second number is going to be a diameter in 14 thousandths. So that defines how large of a circular tolerance zone you have based on the diameter. And then you're going to start to see datums. And if you see an M with a circle around it, that means maximum material is allowed. Bonus tolerance is allowed. And if you see a letter L with a circle, that means least material condition, bonus tolerance applies. But in this top section, we're only referencing datums B and datum C, which on the angle block is the bottom surface here and the side surface. So we're talking about the true position of this hole relative to these two surfaces. The next symbol is the same thing relative to datums B and datum C, but bonus tolerance is allowed when you see this maximum material. It's called a modifier. So that means if we measure the diameter of the hole and it's within spec, but it's on the larger side of the spec, we can get a little bonus tolerance in the position error, which I demonstrated in the last video. And then this last one, it's the same thing as the previous symbol, but it actually adds datum A. And I didn't really talk about how to handle this situation. The calculator is really set up for a two datum system. It's not really set up to measure the third datum easily. So I want to show you how to do that when you have a third datum. And datum A on the print is this back surface. Let's see if we can. It's not here on this print, but if you look at the angle block print, you'll see somewhere that datum A is called out as the back face. So how do we do that up? Well, datum A is our primary datum. So we want to put that on our surface plate. And then what I like to do, as I mentioned, it's hard to do that calculator for 3 dimensions, but it's easier to do with 2. What I'll do is I'll split up the tolerance into my BC datum tolerance and my A datum tolerance, and I'll be using a pin for that. So with my B and C datum, I have 14 thousandths. And if I add in A, I have to account for that as well. So how we're going to do that, once we measure datum B and datum C, I think it was about 9 thousandths from the video. I can't remember exactly. But we're going to measure how much out of perpendicular. Let me flip over to the second monitor. We're going to measure how straight this pin is relative to my part resting on datum A and my pin registered in the hole is the largest pin. So whatever angle this hole is at, the pin is going to tell me. So I'm going to add that to my error. So I'm going to push my part into the pin and apply a little bit of pressure. And this is a little bit tricky because you have to be able to do this without bumping the indicator. But I'm going to zero my pin at the bottom, and then I'm going to run up the length of the pin, and I'm going to look for indicator movement. And I saw about a 1/2 thousandths from top to bottom. If I go back down, I'm getting a repeatable measurement of about a 1/2 thousandths along the length of that pin. Now you don't have to use the pin. If you can run the indicator directly in the hole, that should also tell you how straight the hole is. That can be hard with a very small hole like this one, but with a larger hole, you might be able to get it in there. If you wanted to do the true position of a larger hole, you might be able to get it in there, but you're going to run into the body of the indicator on the top surface. So if you have a longer indicator needle, maybe you can stylus, maybe you can get it at an angle that doesn't interfere, but in practicality, it's a lot easier to put a pin in. And I know that this pin is roughly 2 inches, which is great because our part is roughly 1 inch. So if I wanted to know the perpendicularity error of this hole and add that to my true position error, if my hole length is 1 inch, I want to measure a 1 inch travel on the pin as well. Now, if this pin were longer, let's say we're 4 or 5 inches, and I measured that entire 4 or 5 inch length of the pin sticking out, well, I'm going to get more and more error. But in reality, our hole is an inch long, so I'm going to use an inch long measurement with a pin. And it just happens to work out that most pins available are 2 inches long, give or take, and I happen to have a 1 inch thick part. So it works out that, fortunately it works out, I can just measure the length of this pin. And that would be my A component of the true position. So whatever I measured position-wise for B and C off of the bottom and the side face, I get a true position with the calculator I showed you. Here you can put all that information in and calculate your true position, and then just add whatever you got with your indicator for the A position. So this is one way to do it with a surface plate for 3 dimensions. If you're not going to do it on a surface plate, or sorry, 3 datums, for 3 datums. If you're not going to do it on a surface plate, you can use a CMM. That's pretty much going to be your only options, a CMM or a surface plate. We don't always want to use the CMM, right? We want to be able to use surface plate. And if you have a large enough tolerance, like 14 thousandths is a pretty big true position tolerance, and your part, if it's made in a very good, with good practices and everything's square, everything's parallel, you're not going to see a lot of error here. But if I saw 7 or 8 thousandths in one direction or another, I'd have to go up and rotate around and check every 90 degrees, which again I neglected to do. So this hole could be bent in multiple directions. So why don't I do it again? So I got about a 1/2 thousandths. I think this was the original orientation I did. Oops. I went too far with the indicator and bumped it. So I'm at 0 and rotating up, and I got about a 1/2 thousandths. And now I'm going to rotate my part and check another orientation. You may want to do 2 or 3 orientations depending on how big the hole is, and look for the pin bending one way or another. And again, I get even probably less than a 1/2 thousandths this time, maybe just 1 or 2 tenths. So most of the error is probably in this direction and not as much in this direction. But again, that pin is leaning one way or another, and this is a pretty easy way to check if it's straight and then add that to your 2-dimensional error to get that 3rd component. So when you're talking about a 3-dimension error, we're talking about a cylindrical error instead of just a circle, and every point in your center line needs to be within that cylinder, that maximum cylinder, and if it is, then you're fine. So it's the same thing. It just means that you can't be at an angle. Another way to do this, if you wanted to do it without using the pin, and you could check the true position on this side of the hole from the bottom to the side, turn it around and check it from this side and the bottom as well. And if it's the same from end to end, then you know it's relatively straight. If it's not same end to end, you know you have a problem. So you could, another way you could do this, I'm just thinking out loud right now, is you could you could zero it on one side. Actually, I haven't swept it yet, so I could zero it on this side. I have 0 on my indicator at the top of the pin, and then I flip it around. And do I still have 0? No, I do not. I have about 2 thousandths difference. And we can flip it to this side and check. So this may be a better way to do it, although we're not referencing datum A anymore, but I am checking if the hole is straight. So I have 0, flip it around, and I have about almost 1,000th of error. But once again, this is telling me how parallel it is to datum C. This one is telling me how parallel it is to datum B. Logic would tell us that has something to do with datum A, but that's not always the case, right? Datum A may not be perfectly perpendicular to these faces, which is where things get a little complicated. You're making that assumption, so you could verify that. You could kind of go down a rabbit hole, but you know, if you checked it this way and there was a difference, and you check it this way and there's a difference, and you check it this way, this will probably be the best way to do it. Check this way, and you'll just add this to your two-dimensional position error. So when you have tight tolerance, it's a little more important to do all this. When you have an open tolerance like 14 thousandths, which it's not incredibly open, but if the part was manufactured in a repeatable manner, it should be okay to check it this way. So however you want to check it, however you want to do it is up to you. Just remember that this part hole has to be in tolerance at every piece, you know, from top to bottom, from end to end. So those are a few ways you can double check that the three-dimensional position is correct. Now maybe you only have two dimensions to work with on some prints, and they won't care about that third datum, but a lot of them actually will. A lot of them will call out datums A, B, and C to really rigidly control the position of that hole and make sure that it's straight and perpendicular to what it needs to be. So some of the prints you might see will have the maximum material modifier with 2 dimensions. Another one I've uploaded has all 3. Just depends on the situation that you have. And here I just want to clarify, I had this in the last video, but there's no maximum material bonus tolerance called out for any of these. What's changing here is the nominal diameter of our maximum diameter of our circular zone. So the 10,000th zone is this smaller circle. The 14,000th zone is this circle that happens to line up with the box like we talked about. And the 20,000ths goes even larger, although this, I probably don't have this exactly to scale, just for reference representation. So just remember that the difference in these circle sizes has nothing to do with maximum material condition being added. If it did get added, then you could potentially grow your tolerance even more. All 3 of these could grow even more depending on your hole diameter. So I don't think I was totally clear on that in the first video. I may have implied that some of these are maximum material defined and none of these are. These are just the engineer wants it controlled within a 10,000th diameter, a 14,000th diameter, or a 20,000th diameter. And they could add maximum material. They could add a third datum if they wanted to. So just be aware of that and learn how to read your feature control frames. The next kind of cleanup topic I wanted to discuss is, you know, throughout all of these examples, I've been talking about holes, because holes are what position is going to be applied to most often. And it's kind of the easiest to understand. It's the easiest for me to draw and visualize like I did in the last video. But position can be applied to pretty much any feature that it's valid for. So shaft, like a round extrusion, You know, you could have a round extrusion on a part that needs to be controlled by a position. It could be a key shape, like a square key, a rectangular key, hexagonal key. If it's defined by its center point and its size, then it can be defined by true position as well. So it's not just holes. Sometimes it's positive features or negative features, and it's actually sometimes only in one dimension. So when if it's called out to datums B and C, it's two dimensions. But if you just need something relative to one datum, for example, this we might want to control. What the heck? I seem to have lost the ability to switch over. There we go. So it's not on the print, but if we wanted to control this slot relative to datum A, and we really didn't care about datums B or C, well, we could call a true position, which is by nominal, it's 0.5 on the angle block drawing. We could call a true position relative to A, and then what happens is your circle, instead of being a circular tolerance zone in 2 dimensions, it just gets flattened into a line, and now you have a linear tolerance zone, pretty much just like your plus and minus. There's no difference. So we don't often see a position called out in just relative to one datum, but the best one I could think of, if let me grab if I have this part here and I needed a slot along the side, right, some sort of milled slot, and I want it center line to the axis. I don't want it off center in this direction, and I don't want it twisted. You may call a single datum to control that. So how would that, let me try to draw that. So taking a side view of this part without all the grooves. That's pretty much what that part looks like if you remove all those grooves. You may need a keyway slot, and you may want it to be centered. And you may, be defining this diameter as datum A. So you may want to control this size of this slot and the position with a true position symbol of, let's say 0.01. We'll make it open tolerance. And this is going to control the side-to-side motion as well as the twist, because it could be a little bit twisted and still be within tolerance. Basically, you're going to end up with a zone. You're going to end up with a zone for that center point of the slot in this direction to move left and right. So you could control that with a plus minus, but that would also work. I've seen it both ways. Sorry, it's not in the shot. I've seen it both ways. True position 0.01 datum A. The outside diameter is datum A, and you're just trying to control where that slot sits relative in this direction as well as the twist. So that might be one application that I've actually seen, and there's probably more. I'm sure people can think of some if they, from their own industry. I just haven't seen everything. So I have my little cheat sheet over here. That's why I keep looking. And that's pretty much it. I wanted to kind of explain and make sure you understand some of those details, some of those nuances for 3 datums, 2 datums, and 1 datum, and when maximum material applies. When you're talking about least material, you're talking about extrusions and shafts, and or positive features. And when those positive features are at their least material, that means there's the most slop for the position to have a little extra bonus tolerance. So anyway, I hope that makes sense. I hope you guys like these videos. Please check out the website, Pragmatic Metrology, for more of these videos. And thank you for watching. We'll see you for the next one.